Welcome back to the course on blockchain. So, in the last class, we were discussing about this Algorand protocol in details, which scales up Byzantine agreement for cryptocurrencies. So, they develop a scalable protocol for ensuring consensus in a Byzantine agreement based architecture. So, we have looked into the basic features of Algorand. So, these basic features of Algorand that comprises of having Byzantine agreement based protocol for the consensus by utilizing the gossip based communication protocol. And we have looked into the objectives of Algorand, which states that the protocol need to be fork free. So, you want to avoid the number of forks which are there, so that protocol finality can be ensured. The another requirement for Algorand is to ensure transaction scalability in the presence of million number of nodes, and at the same time supporting large number of transactions per second in terms of transaction throughput. So, with that objective, we have seen that Algorand has three basic steps that it executes one after another. First, it selects a random user from a group of users, which can be malicious or normal. So, as we have mentioned earlier that in a typical network, the majority of the users cannot be adversary. That way, we have assumed that majority of the nodes in the network are honest nodes, and some nodes are adversary. So, whenever you are selecting a user among a set of user randomly, then there is a possibility that the user is either an honest user or a adversary. So, with this particular model in mind, Algorand proposes some steps to ensure consensus finality. So, it selects a random user whose task is to prepare a new block and then propagate the new block in the form of gossiping, and then from the remaining set of users, we select random committee members, and the task of this random committee members is to validate that particular block by running the Byzantine agreement protocol. And then digitally sign the result and propagate the digital signature in the network with the help of gossiping. Again, if you can see that for a particular block that have been proposed in the network, there are more than certain number of signatures floating in the network, then you can be assured that the block has been reached into the consensus, and you can adapt that block to your existing blockchain. And that way, you have the advantage that at every individual round of the protocol, we select different set of nodes for the committee member. So, that is the beauty, or that is the typical feature inside the Algorand mechanism. So, we use something called a cryptographic sorting mechanism that select different number of users. Even the total number of users in a committee may be different at different round of the protocol. So, whenever you are selecting a single user for a block proposal and block propagation, that varies from different different routes, and at the same time the committee members also differ at different routes. So, that way the problem which was there with Bitcoin based protocol, that the entire consensus mechanism can be focused on some predefined number of blockchain miners or Bitcoin miners. So, we have seen that around 5 number of Bitcoin miners, the entire consensus mechanism or the entire mining procedure gets concentrated among those handful number of miners, and it is easier to find out those mining pools, the location of these mining pools, and tamper the entire protocol. So, that way from this centrality, which was a major drawback for Bitcoin kind of protocols, where the entire mining procedure get concentrated on 5 or 6 different mining pools. From there, we are coming out with the help of this Algorand procedure, where it is a truly random protocol, and at different rounds, a different set of committee members will get selected. Now, the question that we have asked, and we have tried to find out that who select this committee. So, we have seen that we can apply certain algorithm called cryptographic sortition, where each committee member selects himself according to some per user weight. So, for that we apply something called a verifiable random function. So, this verifiable random function is a function. By executing that, every member is electing himself or herself to be a part of the committee members. So, this verifiable random function, it returns a hash and the corresponding proof that the hash has been actually generated by the user who is claiming to be a committee member. So, it is just like you are electing yourself to be a committee member, and whenever you are successful in electing yourself, during that time you are presenting a proof that you have correctly executed the verifiable random function, and by presenting that proof you are proving to the environment or proving to the world that you have actually won the election and you are successful to become a member of the committee for validating a new block or to propose a new block. Then we have looked into the block proposal mechanism. So, during the block proposal, because we are using this cryptographic sortition mechanism where every individual node selects himself or herself for proposing a new block. So, that is why at different round it may happen that more than one number of members they win the race and they are able to elect themselves for proposing a new block. Now, to ensure unnecessary to ensure that we are able to avoid unnecessary block propagation in the network, we discard the messages not having the highest priority seen by the user so far. So, this priority value for block proposal, it is obtained by hashing the hash output of the VRF and concatenated it with the sub user index. So, this total number it ensures the priority of a user. So, whenever you are ready to propose a new block, during that time you wait for certain duration. Within that duration, if you are hearing a new block coming from another user where that user is having highest priority or higher priority compared to you, then you do not propagate your block any further. So, that way we minimize unnecessary block propagation in the network. Now, the waiting time that was calculated equal to lambda STP variance and lambda priority. So, lambda step variance is the variance in how long it takes different user to finish the last step of the Byzantine agreement, and lambda priority is the time taken to gossip the priority and the proof messages among individuals. So, we have seen that on average it is approximately 10 seconds. So, if you wait for approximately 10 seconds, if there is any new block which is floating in the network, you are sure to hear that block. Otherwise, you can propose your new block if you have been selected as an new member for block proposal by the cryptographic sortition algorithm. Now, comes to the Byzantine agreement protocol that we will discuss in today's lecture in details. So, this Byzantine agreement protocol, it is a two-phase protocol. So, in the first phase of Byzantine agreement, it reduces the problem of agreeing on a block to agreement on one of the two options. So, the objective of the Byzantine agreement protocol is to come to an agreement on a block. So, the idea is there that if multiple blocks are flowing in the network and all the blocks are kind of valid block, then you select the block where the user is having the highest priority. The priority is defined as I mentioned earlier with the hash value concatenated with the user subindex, and then select that block and make sure that all the nodes in the committee they are agreeing on the same block of highest priority. Otherwise, if a single user has proposed a new block, then all the members in the committee they will agree on the same block. Now, in Byzantine agreement mechanism in Algorand, they propose two different notions of consensus. So, one notion of consensus is called as final consensus and the second notion of consensus is called as a tentative consensus. So, we have two different notions of consensus, final consensus and tentative consensus. So, if the committee member reaches to a tentative consensus, that means that all the members they have not reached to the consensus. It is just like that the value is a local optimum value or a local consensus value, where a part of the committee member has reached to a consensus. So, you need to execute the protocol in further steps if you are having a tentative consensus. Otherwise, if you have reached to a final consensus, that means the block has been reached to the consensus and the block is ready to be added in the existing blockchain. So, let us look into this notion of final consensus and tentative consensus in little detail. So, before going to the notion of final consensus and tentative consensus, we look into the synchronous model assumption which is done in Algorand. So, Algorand assumes two different type of synchrony, strong synchrony and weak synchrony. So, strong synchrony says that most honest users, so we assume that around 95% of the honest user in the network can send message that will be received by most other honest user within a known time bound. So, the idea of this strong synchrony is similar to the synchronous network assumption, where if you are an honest user and if you are sending a message, then all the honest user in the network, or rather than having this 100% synchrony. So, the strong synchrony says that the majority of the honest users, so around 95% of the honest user in the network, they will receive that message within a predefined time bound. So, in that case, when the network is in strong synchrony, then the adversary cannot control the network for long duration, because this honest user, they will be able to receive the message within a finite time bound, and this strong synchrony assumption, it is required to ensure the liveness of the protocol. So, whenever the adversary takes control of the network, we assume that with this strong synchrony assumption, periodically the network comes into this strong synchrony period, when all the honest users or majority of the honest user will be able to exchange the messages among themselves, and during that time this entire network will come out of liveness due to certain attack from the adversaries. Then comes the notion of weak synchrony. Weak synchrony says that the network can be asynchronous for long. So, whenever we are saying in Algorand that the network can be asynchronous for long, we mean that the entire network is controlled by the adversary. The network is controlled by the adversary. This indicates that the nodes are not being able to send the message within a predefined time bound. So, if you just think about our normal computer network, if the network is running fine, or if the network is not being attacked, during that time if you are sending certain message, we have certain level of quality of service from the network, because of which the message is guaranteed to reach at the destination within a predefined time interval. So, it seldom happens that the network is fine, there is no attack to the network, but still the message is stuck somewhere and it is not been able to reach at the destination. There can be congestion in the network in a normal IP based network, but well, the network comes out of congestion because of the TCP congestion control mechanism that we have. So, that way if you define some kind of realistic time bound, within this realistic time bound it is guaranteed that if the network is not under any kind of attack like a denial of service attack or something like this, then if a honest user sends some message, then all the honest user in the network, or at least the majority of the honest users in the network, they will receive that message. But that is not true when the network is under the control of an adversary. So, certain attacks has been made on top of that network. So, either that can be a denial of service attack or similar kind of network attack, where the honest users are not able to send the messages any further. So, we consider that kind of scenario as a weak synchrony scenario. So, in case of a weak synchrony scenario, the network can be asynchronous for long, where it is entirely controlled by the adversary, but bounded period of time. It is not like that this kind of attack network, it is going for infinite duration. It can go for 10 hours or it can go for 10 days, but after some finite duration it will come out of that attack and it will again reach to this strong synchrony behavior. It will show the strong synchrony behavior. So, when the network is under weak synchrony, Algorand ensures that the protocol is safe. The protocol will never accept a invalid block, but the liveness may get hampered. The liveness will get resumed once the network moves to the strong synchrony phase after a weak synchrony phase. So, we must have a strong synchrony period after a weak synchrony period. So, Algorand is safe under weak synchrony. So, that is the guarantee we are providing under this weak synchrony assumption. So, this is the difference between strong synchrony and weak synchrony, and Algorand assumes that this entire network comes periodically in these two phases, the strong synchrony phases followed by a weak synchrony phases, then again a strong synchrony phase and again a weak synchrony phase, and that way it goes on. So, let us now look into this concept of final consensus and tentative consensus in the context of strong synchrony and weak synchrony network. So, in case of final consensus, one user reaches final consensus when any other user that reaches final or tentative consensus in the same round must agree on the same block value. So, this particular property of final consensus, it ensures the safety property of the protocol. So, we say that any user who reaches to the final consensus, then any other user that reaches either final consensus or tentative consensus, they agree on the same block value. So, this ensures that all the members in the committee which has been selected by the cryptographic sortition algorithm, all the members in the committee has reached to a specific block value. So, the consensus has been reached, and if we go for Byzantine agreement kind of thing, so we say that at least 2/3 of the committee members has reached to this final agreement on that particular block value, and if 2/3 number of nodes has been reached to this final agreement based on this Byzantine agreement protocol, then we say that the protocol is safe and the block that has been reached into consensus, it is in the final consensus. So, it confirms a transaction when a block reaches to the final consensus. So, when a block reaches to the final consensus, that means the transaction which has been proposed inside the block, that transaction is final and that transaction can be executed. So, next we look the concept of tentative consensus. Tentative consensus says that one user reaches tentative consensus when other users may have reached consensus on a different but correct block. So, it is just like that. If I look into this entire committee members, entire set of committee members. So, this is my entire set of committee members, and say two blocks has been proposed. So, one block has been proposed as B1, another block has proposed as B2. Now, say half of the or some numbers of the committee members, they have reached consensus. So, this set of committee members, they have reached consensus on block B1, and other set of nodes, they have reached consensus on block B2. Now, interestingly, in this case both block B1 and block B2 are valid blocks. So, both of them are valid blocks. So, both the blocks are valid blocks, but interestingly not all the members has reached to a particular block value, and 50% of the nodes they have reached to one block value, or it may not be 50%, it may be like half of the members they have reached to a particular block value, and remaining half or remaining members they have reached to a different block value, but both of them are the final block. So, the network has reached to consensus, but this consensus is not final because all the nodes have not reached to the same consensus. So, this kind of consensus we call it as a tentative consensus. So, it says that well we have reached to a consensus, but in this case part of the members they have reached to one they have reached consensus over one block, and part of the members they have reached consensus to a different block. So, that is the notion of tentative consensus. So, if the protocol, if the Byzantine agreement protocol reaches to a tentative consensus, then we ensure that after a certain number of rounds, so the protocol is not final there, we have to execute another round, and after another in the next round the entire protocol will be executed with a different set of committee members selected by the cryptographic sortition mechanism. Okay. So, tentative consensus, so we can have tentative consensus in two cases. The first case is the network is strongly synchronous. When the network is strongly synchronous, during that time adversary may be able to cause Byzantine agreement to reach tentative consensus on a block. So, Byzantine agreement is unable to confirm that the network was strongly synchronous. So, if we look into the previous example, in that case, it may happen that during a strong synchrony period, the adversary has taken control of the network. In that case, the adversary has made somehow this set of nodes to reach on the consensus on block B1. That may be the reason because the adversary has launched certain kind of denial of service attack, because of which block B2 has not been propagated to the users which are there in this set of committee members. And because of which this set of committee members, they have not heard of block B2. So, they have reached to the consensus on block B1. And the second case can be when the network was weakly synchronous. If the network is weakly synchronous, that means the network is anyway under the control of the adversary. So, B star can form multiple forks and reach tentative consensus on two different blocks. So, because the network is under adversary, so it may happen that the adversary has launched certain kind of denial of service attack, where the network got partitioned. Because the network got partitioned, we have multiple forks. So, this multiple fork ensures that one block has been propagated in one part of the node, another block has been propagated in another part of the node, and that way the committee members who are spread in different part of the nodes, they have reached to consensus on two different blocks. So, that can be the reason of a tentative consensus. Now, we ensure that whenever a consensus is reached in Byzantine agreement protocol of Algorand, that consensus is not a final that consensus is not a tentative consensus. If the consensus is a final consensus, then only the block is added to the existing blockchain. Okay. So, to come out of the tentative consensus, we run Byzantine agreement periodically, and in the next round the Byzantine agreement is executed again. So, the assumption here is that the network cannot be under weak synchrony all the times. So, after some time there would be strong synchrony, and the cryptographic sortition ensures that different committee members are selected at different round of the Byzantine agreement protocol. So, if I have one round of Byzantine agreement protocol, and in that round of Byzantine agreement protocol, say committee member C1 was the set of committee members, then in the next round it may happen that a different set of nodes has been selected as a committee member, and there may not be any overlap between C1 and C2. So, that way we ensure that even if the adversary takes control of certain nodes in C1, there would be the nodes in C2 where the adversary cannot control. So, that way it will come out of tentative consensus and eventually reach to the final consensus. And Algorand gives a value or gives a bound on the number of rounds that is required to reach into the final consensus. So, if the network is perfect, then in a single round of the Byzantine agreement protocol, you will reach in the final consensus, otherwise you will require around 8 rounds to reach into the final consensus. So, this second phase of the Byzantine agreement protocol says that every node reaches agreement, either agreeing on a proposed block or agreeing on an empty block. Either they agree on one of the proposed blocks or they agree on some empty block. That means, none of the proposed block can be added to the existing blockchain. So, this is the overall procedure of the Byzantine agreement. So, initially we have a reduction phase. So, this reduction phase applies cryptographic sortition to find out the committee members, the members who will be there in the committee. Then we execute the binary Byzantine agreement protocol. The Byzantine binary agreement protocol says whether to agree on a block or not. Then you count the votes, the number of votes that you have from these committee members. So, if this count vote is equal to the binary Byzantine agreement result, that means everyone has agreed on the same block, then it is a final consensus, otherwise it is a tentative consensus. If it is a tentative consensus, then again you run the same thing in the next round by selecting a new set of committee members. So, that is the broad idea of Algorand, and in summary, Algorand ensures that there is no fork, because we are executing Byzantine agreement protocol. So, after the Byzantine agreement execution is over, you have only a single copy of the block that will get added to the blockchain. So, you do not have any fork. or rather they have shown that the probability of having a fork is indeed extremely low in Algorand. We do not have any minor, anyone can participate in the Algorand procedure, and we have trivial computation. So, you do not require huge amount of resources to participate in the procedure. Then you have no proof of work. So, you have no wastage of resources, you do not need to wait for confirmation. So, whenever you get sufficient number of signatures from the network, you are sure that the block has been added. The computations are trivial, we have a good scalability of the entire protocol, and it provides nice security architecture because of this cryptographic sortition mechanism that different number of committee members and different members are selected as a part of the committee at different round. So, it is difficult for the adversary to take control on the majority of the members in a committee. So, that is about Algorand. So, I have tried to give you a very high level picture of how Algorand works, and if you are interested, you can read the original paper from the author, and there are nice videos in the web from Silvia Micali, one of the designer of Algorand. So, you can look into that videos, that is a nice video to look into, and there are certain theoretical aspects of this entire Algorand protocol, like the theoretical proof about how many number of different rounds you require for the Byzantine agreement to converge to the final consensus, or what is the probability of having a fork in Algorand. So, all these details you can find in the original paper. So, if you are interested, you can certainly look into that. So, that would be an interesting read for you. So, that is all about this particular lecture. Thank you all for attending the class today.